Hey guys, I want to continue with our discussion of 10.4, which is officially called connectivity, but I call this part paths because we're going to dig a little bit better more into this, what we can do with paths, and because they play a very important role in graphs and graph theory. And the first application that I want to do is that we can use paths, or perhaps better even circuits. So I remind you what a circuit is. Circuit is a path that starts and ends at the same point. At the same vertex. So you go around in the graph. You don't have to, I'm not saying that you have to go to every vertex or go through every edge. We will talk about that in the next sessions, but there are special applications for that. And so the length of a circuit, of course, is the length of that path. And we deal only here with simple circuits. And then we mean a simple path. Remember, a simple path is most importantly is that, well, first of all, we work normally in a simple graph, although not always, but so a graph with no multiple edges, no loops, that's a simple graph. Secondly, a simple path means that the path doesn't uses the same edge twice. Okay, it's kind of doubling up. This doubling up is not kind of allowed to. Edges, not vertices. You can go to the same vertices. That's not considered an obstruction, but you don't use the same edge twice. That's a simple path, and the simple circuit is then a path that is simple and that is closed. The closed path is sometimes one say closed path instead of circuit. Now. We have talked about one of the big challenges in graph theory is to check actually whether two graphs are isomorphic. And we have seen a couple of ways of doing that. That was one of the last quizzes on graph isomorphisms. And that we can tell them apart by so-called graph invariants. And that way we know that if they have different graph invariants, they cannot be isomorphic. And then if they have so many graph invariants in common, we might start thinking that they're isomorphic. But I remind you, at this moment of time in this development of graph theory, we still do not yet know a complete collection of invariants that if they all check out, then they are the same. So that's still a major problem. But for us, of course, there are simple things, so we will be able to do this. And I remind you of some of the graph invariants. So what does that mean? A graph invariant means that if a graph is isomorphic to another graph, then it has the same value, that invariant has the same value. And so graph invariants were the degrees, the possible degrees that you have, the list of possible degrees, so many of degree 5, so many of degree 3, etc. The neighbors, the degrees of the neighbors, that was something that we used a lot, the degrees of the neighbors. In the sense that if you have a vertex of a certain degree and its neighbors are certain degrees, three neighbors of degree 2 and 5 neighbors of degree 3, say, then in the other graph, if it wants to be isomorphic, you have to find a same situation. Otherwise, they cannot be isomorphic. Or put differently, a vertex that has a certain, the degree set of its neighbors must be set to in the isomorphism. Remember that it's a renumbering or renaming, or if you want a function or a one-one correspondence between the vertices in the one graph and the vertices in the other graph. I'll do examples in a sec. And what you want is that if you take a vertex in the first graph and it has a certain degree, the degree set of these neighbors, then that vertex has to be sent to a vertex which has the same degree, the neighbors and degrees, the same degrees of neighbors, not the same neighbors, of course, because they're different vertices. But okay, and so the third one is path lengths, and particularly circuit lengths. Let me perhaps make it. It is true also for that, but we will use it for circuits. Meaning that if two graphs are isomorphic, and so I'll give an example in a sec, but let me just say it. If two graphs are isomorphic and one graph has a circuit of length 3, then the other graph must have also a circuit of length 3. And in fact, remember what is a graph isomorphism. So remember what is, if you have a graph G here and a G and H, they have a vertex, right? So an isomorphism is a 1-1 correspondence. So this is a 1-1 correspondence, a bijection, if you want, from the terminology that you learned in discrete math 1, between the vertices. And so in particular, if you have this 1-1 correspondence, must be if there's a path of length 3 here, that these vertices must be mapped to vertices in here, and they must also preserve that path. I mean, remember, an isomorphism does many things, right? If this corresponds to there and this corresponds to there, then if there is an arrow here, there must be an arrow there. And for instance, if this corresponds to this element here, right? Then since there is no arrow, so I said arrow, but it is, I'm sorry, I shouldn't have used that word. What I meant to say is if there is an edge between them, because we're talking about undirected graphs. So sorry, not arrow but edge. So if this vertex goes to this goes to vertex, perhaps let me do this in different colors that you see that my map, you don't confuse my map with my, sorry, let me make this a little bit cleaner. Okay, so here are two graphs that are clearly isomorphic. They look so much the same that you cannot hardly not believe that they are isomorphic, right? But so here would be a map, the 1-1's correspondence. So this would correspond to this. This would correspond to this one. Let me put it like this. And this one would correspond to this one, right? And so what needs to happen is not just you map vertices to vertices, but if there's an edge between two vertices, then the ones that correspond would also have an edge. And these two vertices, for instance, have no edge. Well, the corresponding ones should also not have an edge. That's the condition. And therefore, from that it follows that if you have a path from, say, here length 3, so a triangle if you want, then there must also, these edges, sorry, these vertices must be sent or correspond to vertices in the other graph that also have a triangle, also have a path through them of the same length. That's what means a graph invariant, and therefore the lengths are, particularly this length is an invariant here. The path of length 3, there must be a circuit of length 3, there must be a circuit of length 3. So let me do an example of this, a little bit more less obvious than the here the picture I was just basically saying, but just this moved a little bit the left one, right? But here things get really interesting when you're dealing with graphs that look differently, and that's the danger. Look differently doesn't mean that they are different. Remember, isomorphic means iso, same, morph, shape, same shape. So although they look different shape, they actually are the same shape after a kind of a rearrangement. So here we are. Okay, so far these look very same, but look now at what my edges are. So here we have this edge, this edge, this edge, this edge, and that's like this, and that's like this, and that's like that, and that's like that. And here we have like different situation. And this and that. Okay, so let's use the previous tools to see whether this is isomorphic or not. Okay, and the first thing that we did then, if you remember this, go back, is to look at the degrees. So we have a degree 2 here, degree 3, 3, 3, 3, and 2. What do we have here? 2, 3, 3, 3, 3, and 2. Oh, okay, so that matches. So as far as the degrees are concerned, it checks out. So that makes them possible. Well, there's another graph invariant that I didn't mention, the number of vertices. Obviously, because there has to be correspondence between the two, so they have to be the same number. But that's kind of obvious, so I'm not going to talk about that. And then the next thing we would do was listing neighbors and look at the degrees of the neighbor set. But, so, this one here. Now I'm gonna perhaps do this later, but let me now show you that you can also do this with circuits. Okay, so look at a circuit that I have on the left hand side. So I'll do this in, so I have to do it with this one. Let's do it in green. Okay, so I can go this, that, and that. Okay, that's the circuit of length 4. Now, do you see a circuit of length 4 in this one? Yes, there's a circuit of length 4. So, what does this now mean? And this, is there another circuit of length 4 in this one? Now you could try to search for circuits of length 4 in this guy. And you see there actually is no other one. No, this thing can never be part of a circuit of length 4, because if you go this way and that way, so this is already 2, 3, there's no way going back. And you cannot go back yet, that's too soon. So you cannot go back, so you have to go this way, and then you're too far away. Okay? And this is symmetrical, so whether you go this way or that way doesn't make a difference. So these 2 points can never be part of a circuit of length 4. And therefore this is really the only circuit of length 4. There are more circuits of length 4 here. Here's another one, right? So you could go also this, and that. Is there another one? Oh yeah, there's this one. There are quite a lot actually. Okay. So that already. So the number of circuits of length 4 is different here than here. So so let me point this out here. I'll write it here. Only circuit of length 4. And so here I'll do a second one, I'll do it in light green. So this would be, oh no, sorry, I have to use light green here. That would be this one. So this already tells me different, so at least 2. There are more, I think there are 4. At least 2 circuits of length 4. So this is different, so not isomorphic. These 2 things, this and these 2 things, these 2 statements are different, so not isomorphic. Okay, there are different other reasons, and actually quicker reasons, but I wanted to give this one first because it's a more subtle one. It's namely, there are circuits of length 4 in both, but the number is different. Another thing that is different, by the way, is what I've said. Remember what I've said here is that if you take a circuit, then under the correspondence, a circuit must go to a circuit. Yeah, of course, I forgot to draw the last correspondence, of course, so there was this one corresponds to that one, right? I hope that was clear, okay? And then circuits have to go to circuits. So, in other words, if you think of this from in this direction, there's only one circuit here, and that circuit has to go to, say, this circuit. But the problem is that in this circuit, there is a vertex of degree 2, where in this, all the vertices of degree 3. So that's another thing that distinguishes this circuit of length 4 from this circuit of length 4. So not only the degrees are different, not only there are different quantity, the different number of paths, circuits of length 4, they also have different degrees along the road. Because, look, there are 4 points of the degree 4, and these 4 are connected by a path of length 4, or by a circuit of length 4. These are not. If you want to, oh no, they are actually, sorry, I shouldn't have said that. Oh, okay, so they do. Okay, there's another one. Sorry, I didn't see this one. Apologize. Yes, it's sometimes hard to see everything, right? So this is a part of length 4. So if we want to send, if there would be a correspondence, then this path must go to this path. Now, what about this path then? Well, therefore, perhaps the better argument was this. We have here a circuit of length 4 containing a vertex of degree 2. So we have to find this here too. But we already shown that it's impossible to make a circuit of length 4 go through this point. Okay? But there is another more obvious thing actually that so I don't know whether I'll try to get rid of everything without destroying my, okay, that was successful. That was successful. No, not fully successful. I lost one edge here, right? And that's the only thing I left. And, yeah. There's another guy. Look at, now what about circuits of length 3? A triangle if you want. And they're actually that's because they're triangles, they're easy to recognize. There is none, so none here. I mean, you might have to look a little bit, but as I said, triangles are rather easy to see. And so, but there is definitely one here. So here's a triangle, part of length 3. There's another one, of course, down here. There's another one. But so here we have at least one. So again, this shows that they are not isomorphic. Okay. So, okay. Now, that's nice, of course, if they are not isomorphic. Then we can find this. By the way, now you could ask, what about neighbors and so on? Let's see. I look at the neighbor sets. Are they the same type? Let's quickly look at this. Remember this one that we used in the previous quiz. Well, this is a degree 2 and its neighbors have degree 3. So degree 2 and neighbors have degree 3. So that's similar and the same here. So we cannot distinguish those. What about the degree 3 neighbors? A degree 3 has 2 degree 3 neighbors and 1 degree 2 neighbor. And is that the same here? 1, 2, yes. So here, although I have not really checked it, this would actually not tell them apart. And so if we would not, I would have asked you this 2 graphs in the previous, before we talked about paths, you would have assumed that they were isomorphic and you would have tried to find an isomorphic and you would have gotten stuck. So paths, circuits are very, very subtle tools that can tell apart graphs. So let's now look at another graph. What if they cannot tell apart? So let's see. We have here another graph. It's based on a pentagon. Let me use a bit more fancy coloring. So we have 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. That's a bit too big. 5, okay. And so the edges are, we have an edge this way. So connect them, an edge this way, an edge this way, an edge this way, an edge this way, an edge this way. I think that is it. I'll check it later. I'm taking this from the book textbook if you want to double check it yourself also. And then this goes across like that. Okay. They do not look the same, although they have, again, the same number of vertices, 5, so that's okay. So let's look at the degrees of these vertices. 2, 3, 3, 2, 2. Sanity check. How many degrees of odd degrees should we have? Well, there are 2. That's fine. In the previous one we had 4. That's fine. Why? Because we know that the number of odd degree vertices in total must be an even number. So, okay, that just tells me I calculated correctly. What is happening here? Okay, let me redraw this guy because it was a bit sloppy. So, I'll draw it this way, it doesn't matter. It's symmetric, right? Okay. And so now the degree is there, so I'll do this in red again. 3, 2, 3, 2, 2. The same degrees, so that works out. What about the neighbors of the degrees? Let's look at the degree sets. I'm not going to write it down. This degree 2 neighbor has a degree 3 and a degree 2. This one has a degree 3 and a degree 3. This one is a degree 2 and a degree 3. Okay, so we had 2, 3, 2, 3, and 3, 3, or 2 different combinations. Let's see what we have here. We have 2, 3, okay, we have 3, 3, okay, and we have 2, 3. So again, the same configuration, in the same, and it occurs in both cases the same time, same number of time. What about the 3, the one of degree 3? It has a degree 2, and degree 3 neighbor. This one has a degree 3, a degree 2, and a degree 2 neighbor. And that's exactly what happens here too. This guy has 1 degree 3 neighbor, 2 degree 2 neighbors, and the same there. So again, the configuration is exactly the same. I hope that I went a bit quick over it, but you can double check. So this checks out, this checks out. Now about circuits. Okay. Let's look at now, how do you do this? Well, we look for circuits of length 3. Let's list the circuits of length 3. Now this is a bit of work. circuits of length. Yeah, let me. I'm going to make the table a little bit more this way. So so this here the circuit, and here the one length 3. Okay, let's do the length 3 here for both. So here we have this division line between the two. Okay, the length 3. Now I have to give names to these things, so I'm going to go A, B, C, D, and E, and here I like to use like T, U, V, W, and X. As long as they're different names, and I kind of have a little bit of system to recognize my nodes, then it's fine. So let's look length. What about length 2, by the way? Does there what is a part of length 2? Does it exist? A circuit of length 2? No, because a circuit of length 2 would go from here to there, and it has to go back to the original, so it had to go back. So in a simple graph, you would have to go use the same edge twice, and remember that is not what a simple circuit is supposed to be. So there are no simple circuits of size 1 or 2. But the size 1 would be a loop, but again, in a simple graph we don't accept loops. And if you would have a simple circuit of length 2, it would have to go to the edge and go back to the same edge, because we assume a simple graph. Of course, if there would be multiple edges, we could have taken a different edge. That's a different scenario. But in simple graphs, the first thing that you have to look for is length 3. So triangles. And so you can try a little bit from here. I can go that way. But see, a triangle means you're going to have to return very quickly. So where you go next, you have to return back to A, and that's not possible. Can I here and then go somewhere and then return to A immediately? No. So there seem no triangles here. But there is a triangle here, so I'm not going to do everything, but here's my triangle. So I'll do my triangles in blue. There's this triangle here. Okay. Do we have a triangle here too? Yes, here is a triangle. It's much easier to see here that that's the only triangle. Okay. You have to look a little bit that there is to see that there is no triangle there, but trust me, there isn't. So let's write down what it is. It is B, C, E, B, C, E, B. Okay. Now this one here, I'm gonna write it down first. Is for instance T, W, U, T, and go back to T. Now, of course, since it's a circuit, I can start it at whatever point I want. Okay, keep that in mind. I'm not going to use it yet, but I'm going to change it later. Okay, so these are the only ones, I hope you agree with me, the only ones of length 3. So now the one of length 4. Well, for length 4, I see there are probably a few, right? There's 1, 2. No, this is not 1. No, perhaps it's 1, 2. Oh yeah, this one. 1, 2, 3, 4. There's one here. So let me highlight that one. I'll do this in green. So 1, 2, 3, 4. Is there another one? Up to I don't see it. We can try a little bit. In the meantime, I found, of course, also one in here, but again, it's simpler to see here. So we have this one. So in the other graph, you have to think a little bit more whether there is one of length 4. In the right-hand side graph, it's kind of obvious. It can, if you start from here, you cannot have length 4. So the only ones that can belong to length 4 are these four guys here. These two cannot belong to this one cannot belong to a length 4, right? And the same, I guess, here. This one cannot belong to a length 4. That's actually the only thing that we have to exclude, right? Why? Because if I go from here, then if I go this way, I'm too far away. If I go that way, I'm too close by. Meaning there's only one left. There's a triangle. All right, so it seems again that we have one in each. Now, since I used B before, let me start from B again. So this is B, C, A, D, B. Okay. Remember, we only have to reach the vertices because we are dealing with a simple graph. So what we have here, let's start also from t, w, x, v, and go back to t, of course, right? Remember, a circuit means the beginning and end has to be the same. Okay, that's the only one of length 4. Now, what's the maximum length that we can have? Well, that's not really true. Sorry, we cannot predict what's the biggest length of a circuit, because although there are only 5 vertices, we are allowed to go to a same vertex several times. We are not allowed to go to the same edge several times, remember, because when we say circuit, we always mean simple circuit. So length 5, let's see, is there anything of length 5? And yes, there is one of length 5. I'll do this one in orange. So I can go, wait, let me first do it before I draw it. So this way, this way, this way, this way. No. 1, 2, 3, 4, 5, I think, right? So let's do this. No. What was it I'm going to do? Orange. I lost it again. 1, 2, 3, 4, 5. Yes. And here this one is again much easier. I just walk around. Okay. Now notice that there is possibility of, there is a 6th edge. There are 6 edges. Could we have calculated that without really counting them? Yes, remember, a way to calculate this, you add all these numbers up and divide by 2. The sum of the degrees divided by 2 is the number of edges. Is that the case? Just to keep checks, as I said, this is 3 plus 3 is 6, 2 plus 2 is 6, so altogether 12 divided by 2 is 6, so 6 edges. So the longest length is 6, but there is no part of length 6, right? Because if you think about it, I have to then use this edge, but how can I cannot return, right? We will talk about this particular thing later, why there cannot be of length 6, and the same reason here. Okay, so there's a one length 5. Let me write that up again, starting with B, and then I can write it. There's another thing, of course. There is basically 2 orientations, right? I can go clockwise or counterclockwise, or whatever you call this. The order in which I write it down is free. We're free to choose which order we do. Like, okay, let me choose the order that I was writing down: B, C, and then what is it now? Wait, I lost track of my guy. I mean, B. No. B. I cannot go to C. That's sorry. B to E, and then to C, and then to A, and then to D, and then return to B. Now we said, okay, the order is different, so I started from B and I went then to E. But I could also go from B to D, right? I could have B to D and then from D, but then they have no choice, right? It's path. So then from D to A, from A to C and E. That's actually just this guy written backwards. So that's why writing them up in one direction is going one way to the path, in the other direction is going the other way to the path. So we have not lost any information by doing that. So, okay, so here we have go from T, then we go to V, X, W, U, and T, if you go that way. So, more and more this looks like we are dealing here with something that they are quite isomorphic. They have a lot of invariants the same, right? Here we immediately remember, in this case, the number of graphs of circuits of length 4, and these were different. There was one of length 3, there was none here. So this was, in many respects, we had many things that didn't match up. Here, everything matches up. And then we can use that to our advantage, especially because we have a path of length 5. Remember what this actually means. We will give a name to it later. It's a path that actually goes through every vertex. That's kind of perhaps not something that you would always expect that happens, but that is something we will call later, next section, an Euler path. It's a path that goes through every vertex. And that is very useful because now, remember the conditions of an isomorphism is that degrees have to map to degree. Vertices of a certain degree have to go to correspond to vertex of the same degree and with the same neighbors and so on. So, and paths must be into paths. So the correspondence between this and this guy, if it exists, must send this path to this path. Now, we have seen that there are two ways of going to a path, from this way or that way. That's one thing. And secondly, we can start a path wherever we want. We started at B here, but we could have started at E, C, A, and D. And moreover, remember, in a graph invariant, degrees must go to degrees. Now, B is a degree 3 vertex. T is degree... Oh, T is also degree 3. Oh, I thought I picked something... Oh, okay. By accident, I picked the same. So, let's now think how I can use this. So the first thing is, I find a path that goes through all of them. That's not always that happens, but this is an occasion where it happens. And I'm going to exploit that. And I'm going to say, okay, I'm going to walk through this path. Now, there are two directions, so I have to decide which directions I take. And moreover, I make sure that at any time, I'll do this walk simultaneously if you want. So here I start at B and here I start at T. So sorry, I cannot point to these things simultaneously. So B and T, okay? Both have degree T. E has degree 2, V has degree 2. That's good. Then the next thing that happens in my path is that E goes to B, which has degree 3. Sorry, sorry. I get confused again. Let me write down the degrees of each of these vertices as I go through them. This is degree 3, this is degree 2, this is degree 3, that is degree 2, that is degree 2, and of course that's degree 3. Do this here too. Degree 3, degree 2, degree 2, degree 3, degree 2, degree 3. Aha! I was hoping that the correspondence is these guys correspond to these guys in this order. But that's not possible, because the third guy here would then correspond to this guy, but this has degree 3 and this degree 2. But if I go backwards on this curve, on this path, or the circuit, then the matches up. 3, 2, 3, 2, 2, 3, 3, 2, 3, 2, 2, 3. So that tells me, that's the way the orientation I should follow. So I'm going to rewrite this path as T, U, W, X, V, T. It's the same path, I just walk through it differently. And now, what this advantage is that the degrees correspond to degrees. And therefore, I now predict that the correspondence that I want to have is B goes to T, E goes to U, C goes to W, A goes to X, D goes to V, and B goes to T. Well, that's of course we did that already. Okay, it's tedious, but let's do this. We now have to verify that what we postulate as an isomorphism is an isomorphism, and that involves incidence matrix. So I have to write down the incident matrix. So I need a little bit of space, so I'm gonna now get my correspondence here. B will correspond to T, E corresponds to V, C corresponds to sorry, I was rude. No, it's this one here. See, I was already sorry. E was corresponding to U, right? So sorry, let me get this right because it confuses me. B to T, E to U, E to U, C to W, A corresponds to X. Okay, A to X and D to V. Okay, that's the correspondence that I'm trying to do. I'm going to leave it like this. I'm going to get myself some space here. We don't need these now anymore. Because I have to calculate the incidence matrix, right? So, remember, how does it work? We have, the columns are A, B, C, D, E. Get named by the vertices, and in the same order we do the rows. And remember, what we have to do is we put a 1 if there's a vertex and a 0 otherwise. So there's a vertex from A to C and there's one from A to D, and everything else is a 0. B would have degree 3, so I won't have 3 ones in this my row, and this will be in C, it will connect to D, and it connects to E, and so these two are 0. For C, I need again 3 connections, one to A, one to B, and one to E. Okay, so these are 0. D is 2 connections, one to A and B, so everything else is 0. And finally E. E connects to 2 connections, so 2 ones I need, one in the column B and one in column C, and that's it. I hope you still remember how we make these matrices. This is a matrix, right? I wrote it in a raster, but we will talk about these matrices later, and we'll see how it works. Okay, so that's that. And yeah, and so now what do we need to do? Well, send it to check. Send it to check. Remember, I'm sure that I did not make a mistake. I know that this has to be zeros because there's no loops, and moreover it has to be symmetric along this diagonal, right? And all of that is fine. So what I need to do now, remember what I need to do. I need to make the incident matrix for this graph, but not using the order, alphabetic order, whatever, but the order given by the correspondence that I have in mind, which in this case is the order given by the path where we have to walk the path in this direction, right? It's in this direction that we start, right? Yes, T, U, W, okay. So it's actually, because I have this path, it helps me align everything much better. So T, U, W, X, V. So I repeat, why is this order? Because that's the order in which the path has to be run in the same way as if, because here I started with A. No, sorry, I made a mistake, right guys? Do you see the mistake I made? I started from T, but here I start with A. So A corresponds to X in this thing. So what I said is correct, but I started on the wrong end. So this is the wrong spot. So you have to be very, very careful here. So, okay, if I start from A here, then correspondingly this corresponds to X. So I have to start at X. Okay, so X. And then remember I was going around on my path this way. So after X comes V. So B corresponds to V. No. Wait, did I write it now wrong? B corresponds to T. I guess I erased it now. B has degree 3, so this cannot be V. So let me just so in other words, I am going through my B corresponds to T. How is that even possible? A corresponds to X. Sorry. No. I have to do, I'm sorry, I was trying to be clever, but no, I have to follow this recipe and nothing else. Let me not get distracted by anything else. A goes to X, B goes to T, C goes to W, D goes to V, and E goes to U. So I repeat, I found 2 paths that agree, that have the same length and the same degrees as I walk through them. I mean, this path I had to walk in one direction, this in the other direction. Since I erased things, I'm getting a little bit confused now which way direction it was. I think I had it right, and this meant therefore that B corresponds to T, E to U, C to W, A to X, D to V. Meaning that if you walk the path this way, this would be this way, and at the same time you walk the path this way, you get corresponding points. Now this gives you this correspondence. Now here what I did was, perhaps was not smart, but I chose this ordering. I can choose whatever I want. I used alphabetic ordering. Perhaps I should have been smarter and used the ordering given by the path. That's what I didn't do. This is A, B, C, D, E is not a path, right? A, B, there's not even an edge between them two. But okay, I chose this here. As long as whatever I choose here, what needs to be done, and the only thing I need to do is to choose the corresponding vertices in the same order here. And of course, I'm pointing here to the column heads, but the same is true for the rows, right? X, T, W, V, and U. And now I make the incidence matrix using these columns. So X, let's look at X. What is X? X connects to V and W, right? So a 1 here and a 1 there, and everything else has to be a 0. T should have 3 points in there. T has a U connects to U, connects to V, and connects to W. By the way, I'm no longer looking at the paths, right? I'm really now looking at the graph. So perhaps I should have gotten rid of all my colors again. Let's see whether this works. Wow, that went well, and that didn't go well. And then here, let's do the same thing here. Lost something. I lost too much. This one, I even lost my dot here. Okay. Right, so these were 2 zeros. Then W connects to U, to T, and to X. Okay, and so 0, 0 here. So what we can already take a little peek on the left hand side, because what has to happen, this row should be the same as this row. Yeah, that's the case. This row, same as that row. Yay, this, that. But we have to keep going, at least one more row. V in this graph corresponds to T and X. So I have a 1 in the T column and in the X column and zeros elsewhere. Does this now correspond? And only now I can look at it. 1, 1, 0, 0. Yep. And what about the last row? It has to, because it is because of symmetry, right? If you want, you can double check it. But so in other words, we see U connects to T and W. So, and that is of course the same as this. So we have found isomorphism. Okay. And then another thing now that I want to talk a little bit about is these incidence matrices. I want to say a little bit more about these incidence matrices. And I'm going to do a very silly example first. Let's take a graph with only 3 vertices, and that is, let's call this A, B, and C, and suppose that this is how they connect. So it's not even a triangle here. So by the way, notice that this graph has no circuits. That's also possible, right? And we will talk about what these things are. And they also have a name, but let me not give that name yet. Okay, so let's make the incident matrix of this graph. So A, B, C, A, B, C. Of course, it's going to be extremely simple. Yeah, okay. Okay, yeah, no, let's do this. Okay. What is there? Well, A and B, right? And B and A, and this is 0, 0, 0, 0, 0, 0, 0. So let's write them as a matrix. So the incident matrix is 0, 1, 0, 1, 0, 0, and 0, 0, 0. So let's call this the matrix A. That's the incidence. Remember, this is called the incidence. Oh, is it called the adjacency matrix? Sorry, these names are, I'm not so familiar with these names, and sometimes I might confuse them. Adjacency matrix. So I was saying incidence matrix. That's incidence matrix is the matrix where you have rows are the edges labeled by the columns are labeled by the edges, and the rows are labeled by the vertices. Sorry, it's adjacency matrix. So whatever I said in previously, and I mentioned adjacency matrix, I meant incidence matrix, I meant adjacency matrix. Adjacency matrix. This is what we calculated here, right? So these are the 2 adjacency matrices. Okay, so that's that. Now I hope everybody knows what matrix multiplication is. So I want to calculate a square. So I want to multiply this matrix with itself. Okay, what do we get? Remember how this works. To calculate each of these 9 entries, because there are 3 by 3 matrices, we have to go through the corresponding row and the corresponding column. So for the first element, we go through this row, and simultaneously to this column and multiply the corresponding entries. So this entry with this entry with that, this entry with that, and then add them all up. So this would be 0 times 0 times 1 plus 0 times 0, so 1. Okay, then the second one, so for this one, we would have to take still this, it's in this row and it's in this column, right? This element is in the first row, second column, so you use the first row, the second column. You multiply this. If you multiply these with these, I hope you see that result is 0 each time. So we get a 0 there. And the same is true simply because this column is already 0. Whatever you multiply, it's going to be 0 there, right? So we get 0 here. So what happens, this element, if how do I calculate this element? Well, that's in the second row and the first column. So these are the two guys have to multiply with each other. But I hope you see again the result is 0. Something else happens here. Now this element is the second row, second column, so we need the second row in the first matrix, the second column in the second matrix. The order in which you multiply matrices is important because the first matrix is about uses the row and the second matrix uses the column. So second row, second column, and multiplying them, the first two multiply to 1 and the next two multiply to 0, but if you add it all up you get a 1. And if you continue to do this, I hope that's again clear that it's 0. And I also hope that you see now, if I do this here, if I multiply anything here, I would have to multiply this with this column, this column, this column, but of course it's all 0, so the result is going to be 0 here. So I get this matrix. Now this, I can think of this as an adjacency matrix, but it's no longer of a simple graph because I have now a 1 here. Okay, what does this mean? This means there's a loop here. This is also a loop. Now, what does this represent? Well, it represents, so in here we had a path from A to B, and this matrix encodes this 1 here that we have here is encoding this path from A to B, right? So, sorry, let me remind you, how did we calculate this, the value of this element? We used these three values and compared them to multiply them with these three values in the same order. And the only contribution was from this one, which represented this edge, and this one, which represented the same edge. But if you think of this as directed graphs, it is clearer, perhaps, that this one means from A to B, and this one, no, sorry, actually, this one would mean them from A to B, sure, yes, and this would mean, sorry, this one here means from B to A. So from A to B and then from B to A. So in other words, it's a path, if we would follow this one and go back, it's not a simple path, but it's not a simple path because we use the same edges twice, but it is a path. And so notice that we have here a path of length 2, which of course is just going from A to A. So this tells me there's one path of length 2, but it's not a simple path, right? And remember, that's why we didn't look at these things, at these circuits here of, I erased this, but remember I said we don't have to look at circuits of length 2, because if we look for simple circuits, that they cannot exist. So this means there is this A lies on a path of length 2. This B lies on a path of length 2, namely the path of length 2 it belongs to is this path. Okay? It's actually not the only path because it also has this path. Okay? Sorry, let me. Oh, guys, sorry. What I drew here, I'm sorry. I didn't want to have this thing because my incident adjacency matrix was exactly for this graph, right? I'm so sorry. This was the graph I had in mind because that's the adjacency matrix I made. C was not connected here. Otherwise, I would have to put a 1 here, right? A 1 and 1 here. I'm sorry about that. I drew the line, but I never intended to have this line here. So we have this thing here. So in other words, what this means is we only have one path of length 2 that goes through A, namely this path. We have one path of length 2 that goes to B, namely this path. And we have 0 paths of length 2 that go from Z to Z. Is there a path from this 0? What does it mean? That means there is no path from A that goes to B of length 2. Okay? So, Yeah. Let's do the other one, the one that I actually had drawn. Sorry, I want to do this as a second example, but I kind of confused myself here. So this is A, B, C. Now I want this guy, so the adjacency matrix will be different, right? I hope you agree that it is now. So we would now have a 1 here at this spot, right? We have now a run between B and C as 1 here too. So we get a 1 here, we get a 0, 1, 0, right? Yes. Okay. So this is now my A again, and let's calculate again A square. So I'm going to do this here. Sorry, it's a little bit, it's easier, I don't have to copy here. So I'm now calculating A square. So A, the adjacency matrix of this graph. Okay. Let's calculate this. I'm going to go a little bit quicker here. So this times that's going to give me a 1, right? Let's see what happens here. If I multiply this with that, everything is 0, so nothing here. This with this also gives me a 1. What else do we have? This with this is going to give me a 0. And now something nice happens. This with this is a 1, 0 plus 1. I get a 2 here. Okay, and then continuing, that with that is a 0. This with that is 1. The next one is 0, and the next one is 1. I hope you follow this. Now, what is the interpretation of this? So I haven't actually told you what I was doing, right? It's you could think of this as an adjacency matrix, but it's actually something better. It tells me how many parts there are of a certain length. And what is the length? Well, length 2 here. So let's look at this middle guy here, this one here. It says there are 2 parts of length 2, and this is, of course, this refers to B, right? This is the row that corresponds to B, that go from B to B. 2 parts of length 2 that go from B to B. And yes, I can go up and then come down, or I can go this way and come back. What about this one? What is this? This is a 1. This corresponds to A and C, right? So there's a part of length one part of length 2 from A to C. Okay, and what does this mean? 1 part of length 2, because this numbers is all about parts of length 2, because I take A square here. Okay, so there's 1 part of length 2 from A to A, namely going back and coming up, going down and going back up. Okay, so what was my point now? Okay, this was an example. We say if A is the adjacency matrix of a graph, and we calculate A to the n, right? So this is again a matrix of the same, well, let me A to the k perhaps. So we have a graph, so the graph is n vertices, say. So our matrix will be an n by n matrix, right? That's the size, right? It's labeled by the vertices. So this, now I take the kth power, any power that I want, second, third, fourth power. And so what I have here, if I have here, say, a vertex, let's call this vertex u, somewhere here, and here we have vertex v. So I'm looking at an arbitrary element inside here, right? And so this quantity here that I get, so it's going to be a number. Actually, it's going to be a positive number. It is the number of paths from u to v. So the number of paths you can go from this u to this v. Now, since our paths are undirected, that's going to be the same number as going from v to u. And that, in other words, what that means is that this matrix is going to be symmetric again, which we see here. It's a symmetric matrix, and that's just a simple property of it. For those that have taken linear algebra, the product of 2 symmetric matrices is again symmetric. In particular, any power of symmetric matrix is symmetric. So that is what this matrix calculates. Now, to take a power of a matrix is a little bit cumbersome, and for that we can use, for instance, Wolfram alpha or something like that. So I want to do one example here, so of a little bit more challenging graph. Let's do one with 4 vertices here, A, B, D, and C. And let's look at this. Okay. So what is the adjacency matrix? A, B, C, D. I draw the lines so that I can better, I don't make mistakes here. Of course, as we see, that's not really how you represent the matrix, but it makes it easier for us. So there's one from A to B and from A to C, so that's what we get here. From B goes to A, connects to A and to D, so the zeros here. C connects to A and to D. C connects to A and to D. And then D connects to A, B and C. Okay, sorry. And okay, symmetric matrix, everything is fine. So the matrix, if you want it, let me write it down as really as a matrix, is 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0. Okay. Okay. So I'm going to show you later how to do this, but let me just take this in the textbook. They say, okay, we have calculated for you a to the fourth. I'll do other examples, but for now I want to first explain what these numbers mean. And this looks like this. A to the fourth looks like this. And we will double check it later, but let's for now just trust me. That's what you do. In a to the fourth, I said it involves matrix calculation, which is time consuming. In fact, we discussed this. It is it's the cube. It's cubic in, so the complexity is O n cubed, where n is the number of rows or columns. In this case, the number of vertices. So it is kind of consuming, right? So it is 64 calculations here. Even n is 4. But okay, so this is what it is. So what is the interpretation now of this? So let's look at two of this, basically zeros and eights, right? So let's look at one of these. Let's see, what does this mean? This 8. What does this 8 mean? Well, it corresponds here to the A row and the D column, right? But by symmetry, of course, it also corresponds. You could also have talk about this 8. What does this mean now? This means there are 8. So this means there are 8 different paths from, why I keep writing from? It is from A to D. Now you say, oh, really? I mean, okay, here is one, right? From A, oh, okay, where's the other one then? To D, or from A, and then from A to D, that's length 2. 3, well, I have to return to get a path of length 4. Now remember, we are not talking about simple paths in this case. We're talking about paths where we can have double edges. So what I drew here, going and coming back along that edge DB, is a valid path. It is a path, okay, and its length is 4. So that is one of the 8 possibilities, and that's perhaps no surprise that there's so many here, right? That because there's so many ways of going back. So another one, an even sillier one, is from D to C, and then from C to D, and then from D to C, and from C to D. Okay, but I mean, okay, I should have perhaps used a little bit smaller thing, but you followed my line, right? I went 4, it's a path of length 4, but I just basically went up and down. But it is a path from, oh no, that's not a path from A to D. Sorry, that's not a path from A to D. No, what I said was not right. So I have to at some point go to D first, right? This is what I drew now, this green one. What does that represent? Okay, so good. What that green path, it's a path of length 4. So where does it appear? Well, let's think of it. It was a path from D to D. What does that mean? Well, this is the D to D. That would be this 8. So let me therefore color this 8 here. This 8 talks about paths that go from D to itself. In other words, circuits. Right? A circuit is same beginning and end point. So the diagonal tells me what are the circuits. So it says there are 8 circuits that start at A of length 4. remember, this is the length of the path. So this is a way of calculating how many circuits are there by just calculating the incidence matrix, the powers of the incidence matrix. So what about paths of length 3, for instance, or circuits of length 3? Let's figure that out. So for now, then therefore I have to go to I have to use now Wolfram Alpha, because otherwise multiplying matrices is very cumbersome. So here is my matrix, and it is even in Wolfram Alpha cumbersome to put it down, because especially if you have an iPad, you see this is how matrices are input. You put row by row. So I need to put the first row, which is 0, 1, 1, 0. So the entries are separated by commas, and then the parentheses close, open and close, gives me the first row. And now I have to put the second row, which was 1, 0, 0, 1. Okay, and all the while make sure that I have the right commas here between or not. So this row is again at the same 1, 0, 0, 1. Shoo, and then hopefully I do it all right. 0, 1, 0. That one, and close, because I have to make sure they're close. Now that's the matrix, and now I want to take the power. So let's first check that what they told us was correct. Okay, so you can always, from Wolfram Alpha tells you always whether you input it right, because the first thing it says, this is what you told me to do, input. You see here? Yeah. And the output is, well, you say, oh, this is different. No, the 8 in front of there is exactly that. In a matrix, you can factor out a common factor out of all the entries. So if you multiply it back out, all the entries becomes 8. Okay, so this is exactly what the textbook, or what I had written down. But let's now look at 3. So what this will tell us, so what I'm calculating now before we look at it, is the number of paths of length 3 between two given vertices. Okay, ready for this? Okay, I guess I have to put it here. We go. Hello, are you doing? Okay, so is that what you want? Yes, that's what I want. So notice, on the diagonal it is zeros. What does that mean? Now remember, what's in the diagonal? And the diagonal is a path that goes from the vertex to itself. In other words, the circuits. So on the diagonals we would be able to find out how many circuits there are of that particular length. And it tells me there are 0 of them. Okay, so and you can see this graph, we'll go back to the graph in a sec, has no paths of length 3. There are no triangles, there's no circuits of length 3. But of course it has paths of length 3, namely, for instance, the second entry, sorry, I cannot point here, my pointer doesn't work. Okay, I guess I can share it with my Notability. Okay, let me do that. Okay. Done. Okay, let's go now, look at it. Where is it? Yeah, here we are. So here, this entry here, what does this mean? Let me make this a bit bigger. Okay. Oh, no, sorry. The resolution is not very great, so I'm going to make it a little bit. So this is, no, it's still legible, right? So let's look at this entry. What does this entry mean? This is the entry that corresponds to A and B. So this tells me, don't forget there's a 4 here, this tells me there are 4 paths between A and, from A to B, or between A and B, because either way we go, it's the same, right, between A and B. 4 paths of length 3, because this is A cubed, right, of length 3, between A and B, okay? So a good challenge, therefore, would be to do this here. Our original one, we were calculating, and we said there's one circle of length 2, one circle of length 3, one circle of length 4. So we have the incidence matrix, so it's a little bit challenging, so I'm going to use this incidence matrix. And to show you there was exactly one path of length 5, we'll calculate a to the 5th of this incidence matrix. Okay? So But my problem is that I have to do this on two different... Okay, sorry, I have only my iPad to work on, right? I mean, I could do it on my other computer, but then you don't see what I'm doing. So I'm gonna just copy for now very quickly on a piece of paper this matrix, because I have to input it, right, in Wolfram Alpha. Wolfram Alpha, what was I saying? Make sure that I don't copy this wrong. Oh, see, I was already copying this wrong. 0, 0. No, I did something wrong. Oh, this is the one here. See? 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0. Sorry about that. Okay, so let's go to my Wolfram Alpha. I'm gonna I hope that I can repurpose a little bit of my things here. So the first one is 0, 0, 1, 1, 0. So if I put an extra 0 here, I'll be fine. So 0, 0. No, that's too many. Only one of them. So 0, 0, 1, 1, 0. Okay, the next one should be, that's, I have to do this. That has to be 0, 0. That has to be a 1, and then 1 and another 1. Okay, that's my third row. Guys, you pay attention that, and then send me an email later that I made a mistake. But of course, hopefully in the meantime I will have seen that myself too. But it's always possible that I make a mistake here, and then you're always welcome to leave a comment, and then I put a smiley face. Then I remember your name and say, oh, that's a smart guy. He sees that I make mistakes. And so that's this one, and then finally one more row, right? And that would be 0, 1, 1, 0, 0. Okay, and somehow I lost another of my parentheses. Okay, and now path length 5. That's the power, right? Okay, here we go. Whoa, that's quite a lot here, right? And so again, the 2 here actually tells me that there is... Well, that's not good news, right? Because it says there are different number of parts of that line. Oh yes, because, right, because remember, the problem here is that we're counting not simple circuits, but we're counting any kind of circuit. So in this count, it's a bit misleading. It seems like, okay, from A to A, just looking at the number here, there are 2 times 2, right? Because don't forget there's a 2x outside here. So we're looking at the top left element of my... okay, let me again perhaps... how did I do this the other time? Oh, okay, yeah, share. The pretty lady you saw, that was my wife. She's nearby, I guess, with her phone, and that's why you see it here. Okay, import. Done. Okay, and so... Here we go. So let me make a bit bigger. So we are now talking about this guy, right? I'm talking about this 2 here. So this, or actually 4. This is actually 4, right? Because it's 2 times 2. What does this represent? This was a to the 5th. Okay. So what does this represent is, from A to A, there are 4 circuits, because it's a circuit, right? Because from A to A, containing A. Of length 5. Now, one of them we know is it's the one that I have, well, I don't think I have drawn it anymore, but let me redraw it quickly. It was the one, well, okay, so is it 1, 2, 3, 4, 5, that was the one. There was only one. Why are there more? This is 1, we found 1. Why it says are 4? Because, of course, there are other things we can do. You have to think a little bit, how would it work? What else can I do? Length 5. I can now do a circuit that is not simple, right? So I am allowed to walk back on the same edge, but honestly, this is kind of weird. I don't see how to do this. No, that must be. Yeah, no, A is one of the two. No, A corresponds to X. So it's sometimes a bit better to see here, right, on this one. So remember, A corresponds to X. So this would also be there for apply, because again, these are invariants, right? So in X, what are the paths of length 5 to X? Okay, 1, 2, 1, 2, 3, 4. I don't really understand why this number. Did I perhaps put in something wrong then? No, sorry, I'm looking at the wrong thing. Where's my, here it is. Yeah, from A to A, right? And notice, for instance, from B to B, there are many more from B to B, because that's from B to B, here, from B to B, B corresponds to T, so again it's easier to look at T. Right, so from here, for instance, let me do it on this side here. I see many more for B. It is not surprising that B has more options here, because B corresponds to T, okay? So I'm gonna do it on this side, it's easier to see. So here is one of length 5. 1, 2, 3, 4, 5. And instead of going back and up this way, I could first have done that and that way, or I could have gone up and back this way, could go back and up this way, could have gone back up this way. You see, there's many ways of backing up here that I can in length 5. But I'm a bit surprised, I'm a bit puzzled by this X here. Perhaps am I mistaking this? No, because here we see in 1. So length 5, so one path would be just this one. I guess this is considered a different path now. So there are 2, but where are the 2 other ones? The 4. 1, 2, 3, 4. I cannot do this. That's not allowed. Okay, this kind of baffles me a little bit. I'm sorry about that. But you see that therefore also this information is quite, it gives a lot of information, right? So here in this case we see very different numbers here that appear. I'm really wondering whether this 2 should have been there actually. I just want to go back one more time and see, did I have the right matrix? No, it sounds like the right matrix, right? Yeah, okay, I'm a little bit puzzled by this, but at the moment I cannot really explain why this, I don't see the other ones, perhaps I'm just not seeing it, and I hope you guys see it, that there are other paths here of length 5 that connect A with itself. Okay, I'm going to stop here because it's no point of me to keep saying the same thing and not. All right, but this is actually, this last part on counting the number of paths is not really part of the syllabus, but I wanted you to see it. It shows you where the adjacency matrices, how they are used. Okay. Okay, so that's enough for 10.4. I'm going to assign some more homeworks. The most important thing that we have done here is the first part on using paths and especially circuits, simple circuits, to establish isomorphism or non-isomorphism. And so I'll probably do a quiz on that as well.